In this module, Module 18, we're going to talk about some more CMOS examples. So using transistors to build gates. So first of all, we'll review what NMOS and PMOS transistors are, so the building blocks of our CMOS gates. Then we'll review CMOS gates, particularly that they're each composed of a pull-up network and a pull-down network, where the pull-up network only has PMOS transistors in it, and the pull-down network only has NMOS transistors in it. Okay, so let's get started here. So remember that an NMOS transistor turns on or has its two terminals D and S connected when the gate is 1. A PMOS transistor turns on when its gate is 0. And that's emphasized by the PMOS transistor having a bubble on its gate and the NMOS transistor having no bubble on its gate. Remember that the pull-up network, so the network that connects the output Y to VDD, always consists of PMOS transistors only. The pull-down network that connects the output Y to ground, the pull-down network always consists of only NMOS transistors. So here's an example gate. So let's suppose we have this inverting gate. So we have Y equals some expression that's inverted. This is called an inverting gate. And we know that this is the 4-input NAND function. So we can, probably the easiest way to do this, because of the way it's written, is just to write Y bar equals A and B and C and D, and to build the NMOS network. Well, Y bar is going to be true when A and B and C and D are true. That means that Y is going to be false. So Y is going to be tied to ground when, these variables in an AND relationship. So we know AND means series, A and B and C and D. Remember, this AND relationship means they all have to be true in order to get Y bar to be true, or in other words, Y to be false. Anything in an AND relationship is in series. Okay, so we have our pull-down network, our connection between Y and ground. And now we need our pull-up network. Well, our pull-up network is going to be a complement of the pull-down. Well, the pull-down is in series, so our pull-up will be in parallel. So here's our VDD up here, and we're going to get those in parallel. Again, only PMOS transistors in our pull-up network. We're going to have them tied to the same inputs. And so if we read from our pull-up network, the equation would be Y is going to be true when A bar or B bar or C bar or D bar. In fact, that is the same as our original equation. And again, we could have started by writing this equation using De Morgan's like this, and then implementing the pull-up network first, and then writing the pull-down network. So either way works. All right, so here we have another inverting gate. In other words, Y equals some expression with a bar over it. This is the sum expression in this case. So this is our 4-input NOR gate. Sometimes we write that as NOR 4. And so, again, we could write, we have Y equals something bar. In other words, Y bar equals A or B or C or D. We have an OR relationship. That means parallel. And then we complement those relationships to get the pull-up network. So we have parallel on the bottom. We're going to get series on the top. we're going to get A bar and B bar and C bar and D bar. So now let's do some non-inverting gates. So here is a 4-input AND gate. Sometimes we write that as AND 4, a 4-input AND gate. And again, when we have a non-inverting gate, we know that inverting gates are easier. So we're actually going to build some other intermediate function, the inverted version of the equation, and then we're going to invert it. So first we're going to implement this intermediate function, A and B and C and D, all of that bar, function Z, and our pull-up network is going to be a complement of that. So we have series on the bottom and a parallel on the top, all connected to VDD. And our inputs are always the same to the PMOS network as to the NMOS network. So here we have our 4-input NAND function, and we need to invert it then. So we need to essentially do this, y equals z bar. So it equals A and B and C and D bar. That's z all the bar. Now we just take an inverter, and produce y, what we actually wanted. So at high level, this is basically a 4-input NAND gate at the transistor level, A, B, C, D, fed through an inverter. So again, we could have built this just directly using transistors, but we wouldn't have gotten the minimal solution. So let's show the other way that this is not minimal and not recommended. But I'm going to show it to you anyway, just so you can see the counterexample. So y equals A and B and C and D. So I know I have a AND relationship in my pull up. I'm producing y. So y is going to be true. We're tied to VDD. When A is true, and B is true, and C is true, and D is true. Well, I have A bar, B bar, C bar, D bar on the inputs because of this bubble here. Because the bubble's on the input of the PMOS gate. So when A is true, A bar is false, and it will turn on this transistor. When B is true, B bar is false, and it will turn that transistor on. When C is true, C bar is false. When D is true, D bar is false, and we'll turn on that transistor. So when A and B and C and D are all true, we'll get a connection, in fact, from VDD to Y. And now we build the NMOS network. Well, PMOS was in series, so our NMOS is going to be in parallel. And always tied to ground. And remember, our inputs for our NMOS and our PMOS networks are always the same. So I'll get A bar, B bar, C bar, D bar. And this looks pretty good. In fact, it looks like it's fewer transistors, just 8, instead of the prior implementation, which was 10. But in fact, what we're not showing here is that in order to get A bar, we actually have to have an inverter. That's not just free. And then we could say, this box is equivalent to this symbol. And then we could just say B to get B bar. We have to also put that through an inverter. C to get C bar. I'm drawing the transistor at a higher level of abstraction. I've drawn it once at the low level of abstraction. And I'm using the higher level of abstractions just to save me time. And so instead of 8 transistors, that it actually took us 8 transistors for the function plus 1, 2, 3, 4 inverters, which is 4 times 2, 8 transistors. So this one took me 16 transistors to build instead of the prior version, which only took us 8 transistors plus 2 transistors, 10 transistors. So the take home on this is, if you're given a non-inverting gate, first build the inverting version of that. So put a bar over it and then invert it to use a minimal number of transistors. So here's another non-inverting gate. This is a 3-input OR gate. And so again, to use a minimal number of transistors, we're going to build an intermediate function, the inverted version of that, and then invert it. So A or B or C this is the pull-down network. OR means in parallel. And now our pull-up network, well, pull-down is in parallel, pull-up will be in series. And again, that's actually not Y, that's our intermediate function Z. And so now we have to feed that through an inverter to get our actual function that we want, Y. So now this one took 6 plus 2 transistors, so 6 transistors for the function plus 2 transistors for the inversion, and we get 8 transistors to implement this circuit. Again, you can go through building the less optimal solution. A or B or C, again, would be this. Our pull-up, A or B or C. In order to get A or B or C in the pull-up, we'll have to put bars on our inputs because of our PMOS transistors. And then we'd put our NMOS in series because our PMOS are in parallel. And we would get 6 transistors for the function plus, well, we need A, B, and C, all of those to be inverted. So 3 times 2, another 6 transistors for the inversions. This is 12 transistors instead of 8 transistors of our optimal solution. Again, logically correct, but not minimal. All right, so let's do some more complex inverting gates. So here we have Y equals A and B or C and D. So if it helps, you can invert both sides and get Y bar equals AB or CD. So we want Y to be false when A and B are true, or C and D is true. So Y bar to be true, in other words, Y to be false when A and B. So we have an AND relationship, so that means series. This is series. This is also an AND relationship, that will be in series. And these two are in an OR relationship, so they'll be in parallel. So we get A and B, that's in series. It's in parallel with C and D, which are in series. All right, so there's our pull-down network. And now our pull-up network, we're going to complement it. So A and B were in series. C and D were in series. And those two subnetworks were in parallel. So those two subnetworks will now be in series. A and B will now be in parallel. That network, that subnetwork, network 1 or something, will be in series with network 2. Network 2, C and D was in series. Now those are going to be in parallel. Remember, alternatively, we could also use De Morgan's on this We have y equals a and b, or c and d. Using De Morgan's, that or turns into an and. We get a and b, pull down the terms, and then invert them. Do De Morgan's again, and we're going to get, remember to keep the parentheses, this and turns into an or, pull down the terms, invert them, and then same thing with our second term. So we get a bar or b bar, quantity and, here's our quantity and our series, c bar or d bar. So here's another example. It looks pretty similar to what we had before, but now we have b is inverted. So we're going to do a similar thing though. The structure will be the same. We're going to get our pull down network. So y connecting it to ground will be a and now b bar. So now I need a b bar here instead of a and b like we had before. So a and b bar, or, well, here's our parallel relationship, c and d. And now we have our pull up network, same thing as before. A and b bar were in series, so now they're going to be in parallel. Remember, the inputs of the gates are the same in the PMOS as in the NMOS, so we put a B bar here. Those subnetworks were in parallel, so now they're in series. And we finally have our C and D, which was in series. Now those are going to be in parallel. So this is not an 8 transistor network or gate. It actually is a 10 transistor gate because we also need to show that we don't get B for free. We have to create B using an inverter. So this is our function took 8 transistors plus 2 transistors to invert B. This is a 10 transistor gate. Again, we also could have started with the pull up instead and said y equals, well, let's do De Morgan's on this, or turns into and. We bring down our terms, and then we invert them. And now we do De Morgan's again. We don't forget to keep these associated. This and turns into an or. We bring down our terms. Then we invert them as a second step. This and also turns into an or. We bring down the terms and then invert them. And we could do involution on this and get A bar or B and quantity and C bar or D bar. And so now we can implement the pull up first, where we're going to get A bar, or there's our parallel relationship, A bar or B. Well, in order to get B on a PMOS, I have to put B bar on its gate. And here's our and C bar or D bar. And then I can do the NMOS network as well. So A bar or B parallel, so now those are going to be in series. And we end up with the same result. Again, we have to create our B bar. So we end up with the same result again, a 10 transistor complex gate. So here's another example. We have a complex non-inverting gate. So we're going to do the same thing as we've done before. We're going to say Z is equal to A or B, C, D, and E, all of that bar, and then we'll invert it. So now we're going to get, these are in an OR relationship, and then these are in an AND relationship. We're going to get A or, here's my A or B and C and D. All of that ANDed with E. And now we're going to take these, and you can call these subnetworks if you want. We have this subnetwork, which is in series with this subnetwork. So that means they're going to be in parallel on the top. Okay, so we have these subnetworks in parallel. And now this subnetwork, which is over here, is in parallel. Those are in parallel on the bottom, so they're going to be in series on the top. So we're going to get A in series with this thing. Well, those were in series on the bottom, so now they're going to be in parallel on the top. And so again, that's not actually Y. That is in fact Z that we're creating. In order to get Y, you have to then put it through an inverter. And now we have our solution, which is a 3, 4, 5 transistors for the bottom, plus 5 transistors for the top, 5T for the pull up, 5T for the pull down, plus 2 transistors for the inversion, and we get a 12 transistor solution. So here's another function that we could implement, and we look at it and we can say, oh, well, there's some inverted terms and some not inverted terms. Kind of unclear whether we should perform or implement the inverted version and then use an inverter at the end, or just as is. So there are really always those two choices. So if you're not sure, you can just implement both, and then whichever one uses the fewest transistors, choose that one as the minimal solution. So here we try implementing it directly. We have Y equals A bar. So we get A bar. I'm doing a PMOS network. Or, well, that's a parallel relationship. Or B and C and D bar. That's a series relationship. Or, here's our parallel relationship. Or E bar. And so now we can implement the pull-down network. These are in parallel, so they're going to be in series on the bottom. So we're going to get A, and here's our E. And this middle network, those were in series, so now they're going to be in parallel on the pull-down network. And again, our inputs are going to be the same on the pull-up as the pull-down. And so here we have our gate. But again, remember B bar and C bar, we don't get those for free. And so, we can draw it once and say this inverter is equivalent to this. So I know that what the transistor level view of an inverter looks like. And we need 2 of those inverters to get B bar and to get C bar. So this gate has 10 transistors for the function, plus another 4 transistors to get inverted inputs. And so we have 14 transistors for this complex gate. So we can now try it the other way and basically implement Z equals A bar or BC D bar or E bar, and now we'd implement the NMOS network first, or that would be the easiest way. And so now we're going to get A bar or B and C and D bar, or parallel relationship E bar. And that would give us connection to ground. Oh, that's not Y, that's Z. So we'd get A bar or B and C and D bar or E bar. So I can already tell that this is going to be more transistors because, well, I have 3 inverted inputs instead of just 2. So in the prior implementation, this one on the left, B and C are inverted inputs, so I need 4 extra transistors. In other words, 2 inverters to make those inverted inputs. In this one, I have 3 inverted inputs, A and D and E. So I'm going to need 6 transistors just to make those inverted inputs, and another 2 transistors to invert Z in order to make it equal to Y. So I already know that this solution is not going to be optimal, and in fact, the one on the left is the optimal solution. So here's another example complex gate that we want to build using transistors. And so we can take this equation and go ahead and immediately implement it. We're going to get Y equals, well, A or B bar of A or B bar, and A bar or C, and here's our pull up, and now we're going to implement the pull down. Well, this subnetwork is in series with this subnetwork, which is in series with this subnetwork. So those are going to all be in parallel. Parallel subnetworks. And each of those subnetworks was in parallel, so those will be in series. Okay, we'll get A bar. We'll get A bar B. Remember, the inputs into the pull-up part of the network will be the same as the inputs into the pull-down part of the network. Second one, we're going to get A. So this gate takes 12 transistors for the function, plus I have to draw inverters to get A bar and C bar. So 12 transistors plus 4 transistors to get the inverted inputs, and we get 16 transistors total. So you can consider if the inverted version would be better to implement, and then inverting it using a final inverter on the output. So we could build that, but we can see that in fact this is going to be worse because, well, this is the pull-down network. A or B bar, so we're going to need A, we need an inverter for B, and that's going to be ANDed with A bar C, that's going to be ANDed with D bar or E bar. So there's our pull down network. That's not Y, that's Z now. But I'm not going to even bother doing the pull up network because I know that I'm going to need, well, 12 transistors to perform the function, and then 1, 2, 3, 4 inverters, or another 8 transistors, 4 times 2 transistors to invert inputs. And so now this one's going to require 20 transistors, where the last version just required 16 transistors. So this one would not be optimal. In fact, this would require 20 plus 2 more transistors to invert Z to get Y. So 22 transistors in total. So certainly not the most optimal solution. So here we've gone through several examples of taking, various gates and implementing them using transistors. Remember that we could also go the other direction and we could read off the function of a gate at the transistor level. So for example, this one I could read off as, the easiest way to read off gates for transistor level is from the PMOS, but you could use either. So we could read off the function of a gate from the transistors themselves too. So we could go the other direction. The function of those two transistors is A or B bar. They're in parallel, so they're in OR relationship. And they're in series with the next group of transistors. So series means and. The next group of transistors is A bar or C. Those are in a parallel relationship. So they're in an OR relationship. And the next group is also, so this and is from that series relationship. And the next group is in parallel, would get D bar or E bar. So now we can read our equation as well directly from the transistors themselves.